This is part 5 of further mathematical induction, where we are looking at recursive formula proofs in this video. So in extension 1, we have seen recurrence relations. These are where any given term is defined by terms before it. So a first order recurrence relation just uses the previous term. So for example, some nth term is the term before it, tn minus 1 plus 2. So say for example, we started at 1, right? Say that was our first term. Then the next term is that term plus 2, so it would go up to 3, right? And then 5, 7, and so on. That if we started at 1. Of course, as this stands, with no starting point, there could be lots of different sequences that we could come up with, but that's just an example of a first order. Second order uses the two previous terms. So a famous example that you might be aware of is the Fibonacci sequence. So let's say we start with term 1 being 1 and term 2 being 1. And then from this point forward, we say that any nth term is given as the sum of the previous term with the term before that again. Right? And that's what this leads us to the Fibonacci sequence, where we go, okay, we got 1, then we got 1. Now I'm going to add these two terms together to get 2. And now for this term, I add its two previous terms, so I get 3, then we get 5, 8, and so on. Quite a famous sequence there, the Fibonacci sequence. But that's an example of, right here is an example of a recursive formula that is a second order recursive formula. So we're going to do two examples where we use recursive formulas in our induction proofs. First one will have a first order recursive formula, and our second example will do a second order recursive formula. So let's go. Example 1. Given term 1 equals 3 and term n equals tn minus 1 plus 2, so that's what we were talking about before, right? Prove by induction that term n is equal to 2n plus 1 for all n belonging to the set of natural numbers. Alright, so let's start with step 1. Prove true for n equals 1, which is the smallest natural number in this case. Alright, so t1 equals 3. That's nice and easy. That's already given to us. Right, so that's a given. But then we've got to look at this tn formula. So we've got tn equals 2n plus 1. So when n equals 1, we have t1 equals 2 lots of 1 plus 1. And that's obviously 3, so we're all good. Right? The proposition, what we're trying to prove is true for n equals 1. Okay, step 2. Assume true for n equals k, where k must also be an integer, of course. So we want to say, this one's set up a little bit different to previous inductions, but we're basically saying, okay, given some k term where we've got this recurrence relation of tk minus 1 plus 2, given that, and obviously our starting point that we've already proven, then tk is also equal, or can also be found, by the formula 2k plus 1. Okay, Okay, so that's step 2. Now, step 3. Prove true for n equals k plus 1. So let's write out what we're required to prove, and that is that given tk plus 1 being equal to the term prior, so tk plus 2, given this, then tk plus 1 can also be found 2 lots of k plus 1 plus 1. Okay. Alright, so let's start with our recurrence relation. That is tk plus 1 equals tk plus 2. Let's start with that because now we can use step 2, can't we? Back up here. Step 2, right? We've got this assumption that we can use, that is that the kth term is equal to 2k plus 1. So let's make the substitution here. Right, so we've just used step 2. And when we expand this, we get 2k plus 3. I shouldn't say expand when we collect like terms. But what is it that we're after? We're after 2k plus 2 plus 1. Okay, so 2k plus 3. I mean, look over here. When we expand this back in what we're required to prove, that becomes 2k plus 3, doesn't it? And this is simply 2k plus 3. So, yeah, we're done. It's therefore true for n equals k plus 1. And so then we would finish off with our overall statement that, by the process of mathematical induction, it's true for all values of n. Okay, so that was actually quite a nice step 3, wasn't it? Let's go to our second example now, which is a second order recursive formula. Given t1 equals 1, t2 equals 5, and tn equals 5 lots of tn minus 1 minus 6 lots of tn minus 2. So there's our second order recurrence relation. Alright, we can see it's relying not just on the term before it, but also the term before that. So given these 3 bits of info, prove by induction that tn is equal to 3 to the power of n minus 2 to the power of n. We're going to prove that that's true for all n belonging to the set of natural numbers, but n must be greater than or equal to 3. So, step 1. Prove true for n equals 3. So let's start with our recurrence relation. So we've got tn equal 5 lots of tn minus 1 minus 6 lots of tn minus 2. So what does that mean when n is 3? That means that the third term is 5 lots of the second term minus 6 lots of the first term. And we know term 2 is 5. Okay, so this is 5 lots of 5 minus 6 lots of 1. That's term 1. So what have we got here? 5 5's 25 minus 6, and that gives us 19. Okay, so that's sort of like our left-hand side, I suppose, but we also want to see what happens with this equation. So we also have tn equal to 3 to the power of n minus 2 to the power of n, and so when we're looking at term 3 specifically, this is 3 cubed minus 2 cubed. Well, 3 cubed, that's 27. 2 cubed is 8. And so when we do 27 minus 8, we also get 19. So let's give ourselves a bit more room. We can therefore say that this is true for n equals 3. Alright, step 2. Assume true for n equals k. K must also be a natural number, and just like n, k must be greater than or equal to 3. So what are we saying? We're saying given tk being equal to this recurrence relation, so 5 lots of the term before it, so tk minus 1, minus 6 lots of the term before that, so tk minus 2, given that, then tk is equal to 3 to the power of k minus 2 to the power of k. Alright, seems easy enough. Let's go on to step 3. Prove true for n equals k plus 1. So what are we required to prove here? We're trying to show that if we are given tk plus 1, and we're looking at the recurrence relation here, so that would be 5 lots of the term before it, so tk, minus 6 lots of the term before that, so tk minus 1. Given this, then tk plus 1 can also be found by 3 to the power of k plus 1 minus 2 to the power of k plus 1. So that's what we're required to prove in step 3. Alright, so let's start with the recurrence relation, which is this left-hand bit here. And normally this is where we would go and use step 2, right? Let's have a look up at step 2. So there's our recurrence relation, and we're assuming this to be true. That's tk. So we've got tk here. So we could make this substitution. Right, we could take this and replace it with this. But what about t of k minus 1? We haven't got anything for that. So what are we going to do here? Well, remember how we use the analogy of dominoes, or climbing up the rungs of a ladder when first looking at mathematical induction. In order for any particular domino to fall, the one before it must have fallen. So when we get to step 2 and we assume some generic domino falling, we could have just as easily chosen the domino before that. Right, so if we're assuming that this is true for n equals k, then it must also be true for the domino before. It must be true for n equals k minus 1. So what that means we can do for this kind of question is we can say, okay, I'm going to look at t of k minus 1. So I'm just going to add this into step 2. And so let's apply the recurrence relation to t of k minus 1. So it would be 5 lots of tk minus 2 minus 6 lots of tk minus 3. And if that's true, then we can say tk minus 1 is also equal to 3 to the power of k minus 1 minus 2 to the power of k minus 1. And this is how we can now use step 2 completely to work on step 3. See, normal induction questions, we just go one domino knocks the next. But because of this second order recurrence relation, we're kind of going more along the lines of 2 dominoes together and then knocking the next. So now if we look at here, this tk minus 1, we have the substitution necessary back here in step 2. So for second order recurrence recursive formulas or recurrence relations, whatever you want to say. For second order questions, we actually have two parts to our step 2 that we need to use. Alright, so let's get back into step 3 now, and let's make those appropriate substitutions. So we have 5 lots of tk, which is 3 to the power of k minus 2 to the power of k. And then we can also do our second substitution, where we replace tk minus 1 with this 3 to the power of k minus 1, take away 2 to the power of k minus 1. And now we can set about trying to make this expression look like this. Once we do that, then we have completed step 3. So give ourselves a bit more room, and let's get to it. There's not too much we can do with this first expansion. It's 5 lots of 3 to the k minus 5 lots of 2 to the k. But then what could we do with the second expansion? Well, we've got the minus 6, and let's split this into 3 to the k multiplied by 3 to the power of minus 1. So splitting this power up, and now we've got negative 6 times negative, so this becomes a positive 6 times, and we'll do the same thing, 2 to the power of k times 2 to the power of minus 1. So in both cases here, if we were to put these back together, we would just get what is above. But what is 3 to the minus 1? What is 2 to the minus 1? Well, that's equivalent to 1 on 3, and this is equivalent to 1 on 2. So let's have a think about how that would simplify if we think of it in this way. The first bit doesn't change, so we still have the first two terms remaining the same, but now we've got 6 over 3. So 6 over 3 simplifies to 2, so 2 lots of 3 to the power of k. And likewise, 6 over 2 becomes 3, so we have 3 lots of 2 to the k. And now we can collect like terms. We can focus on the 5 lots of 3 to the k minus the 2 lots of 3 to the k, and we can also focus on the negative 5 lots of 2 to the k plus 3 lots of 2 to the k. So 5 take away 2, that is 3 lots of 3 to the k, and negative 5 plus 3, that is minus 2 lots of 2 to the k. And then using our power rule, so same base and powers, we have 3 to the power of 1 times 3 to the power of k. So this gives us 3 to the power of k plus 1. And likewise we have 2 to the power of 1 times 2 to the power of k. So let's add those powers together. And we've done it. We have 3 to the power of k plus 1, like up here, minus 2 to the power of k plus 1. So we can say that this is therefore true for n equals k plus 1. And after we do our final statement, we are finished. Great job.